Okay, so good morning. This is our 14th lecture of the course Compressible Flow and Gas Dynamics. In the previous lecture, we started our discussion on one-dimensional flow with friction, which is popularly also known as Fanno line flow. If you do remember, we have first included the frictional effect into our momentum equation, and then we have tried to further simplify this momentum equation, particularly the case of a thermally perfect gas. Okay, and if you do remember, finally we have obtained the equation which is 4f bar L by D equal to okay okay, so this is the equation which we have actually derived in the last lecture, and particularly one important aspect I have considered, that when we are considering this fanning friction factor F, I am representing F bar as nothing but 1 by L integral of F x dx, because f will be function of x, so that this I have considered nothing but the length averaged fanning friction factor. Okay, so up to this point we have studied in the last lecture. So meaning is very simple. From this equation I can simply interpret that for a calorically perfect gas, if m1 is the upstream Mach number and if f bar is the frictional average fanning friction factor and L is the length of the pipeline and D is its diameter, then I can determine what will be the downstream Mach number M2. Okay, so that is something which we can actually predict from this particular equation. Now, along with this downstream Mach number, we have to also determine nothing but the other properties such as density, temperature, then pressure, stagnation pressure and stagnation temperature. Okay, so these other properties also we have to determine at station 2. At station 1 we are considering that these are known to us, and then we are having flow inside a pipe where friction is actually involved, so that friction will actually change all the properties at the exit point. So we need to now determine these properties. So let's try to see this particular equation. If you see, this is nothing but the outcome of momentum equation. Okay, this is the outcome of momentum equation. Now let's consider the energy equation. So as per energy equation, we will be having h1 plus v1 square by 2 will be equal to h2 plus v2 square by 2. The reason is very simple. We don't have any addition of heat and removal of heat, and we are not doing any work transfer during this particular process. So that's why whatever we are having energy, that will be just part of enthalpy and the kinetic energy of the fluid. Okay, and simply from here I can say that h plus v square by 2 is equal to constant, and h plus v square by 2, as per our earlier understanding, I can also call this as nothing but the stagnation or total enthalpy. So I can say h naught equal to constant. In the similar way, because I am considering now this particular case for a calorically perfect gas, so in place of H I can write Cp into T plus V square by 2 equal to constant, which will give me Cp times T naught equal to constant, and as for calorically perfect gas Cp is also a constant, then I can say from here that T naught equal to constant. Okay, so this is very clear that unlike the case of a heat transfer, so in case of heat transfer what was happening, enthalpy as well as the total enthalpy as well as the total temperature were actually increasing. But over here we are not having any addition or removal of heat. The process of flow through a pipe is actually completely adiabatic. So in this situation what we are finding? We are finding that total enthalpy and total temperature are nothing but remaining the constant. Okay. Now what we need to do? So if you do remember, we have, so from here I can simply say that T01 will be equal to T02. Okay, and this I can say call it as a T0. Now we have seen earlier while we derived the different forms of energy equation and try to establish the stagnation properties, that T0 equal to T times of 1 plus gamma minus 1 by 2 into m square. Okay, so that is something which we have seen earlier. So from here I can simply say that, because T01 equal to T02, so I can say that T1 times 1 plus gamma minus 1 by 2 m1 square equal to T2 times 1 plus gamma minus 1 by 2 m2 square. And from here if I do further simplify, I will be finding T2 by T1 will be equal to 2 plus gamma minus 1 into m1 square divided by 2 plus gamma minus 1 into m2 square, and 2 will be cancelling out in the denominator. So this will be my ratio of T2 by T1. Okay, so it means that from this first equation, say this is my equation number 1, from this first equation, if I know the average fanning friction factor, length of pipe, diameter of pipe, I can calculate value of m2 correspond for given value of m1, and then I can utilize this particular equation to calculate the value of T2, because T1 will be known to me, and for given value of m1 I can calculate T2. Okay, now let's try to find out the value of pressure. So we also have one important relation from continuity equation, that rho 1 v1 is equal to rho 2 v2. Okay, and for calorically perfect gas I can write rho 1 as nothing but P1 by RT1, and in place of v1 I can write Mach number of 1 into a1. Okay, because my velocity Mach number is velocity by a, so velocity will be equal to Mach number into a. Similarly I can write on the right hand side P2 by R T2, and this will be m2 times a2. Okay, now once again for calorically perfect gas I can write P1 by RT1 into m1, and in place of a1 I can write square root of gamma r t1. Okay, and this will be equal to P2 by RT2, and then m2 times square root of gamma r t2, and this if I further simplify, from here I will get P1 by P1 m1 by square root of T1 equal to P2 m2 by square root of T2. Okay, so now my aim is to find out the value of P2 by P1. So if I calculate P2 by P1, it will become P2 by P1 is equal to m1 by m2 into square root of T2 by T1. So we have just now calculated T2 by T1. So P2 by P1 will become m1 divided by m2 times 2 plus divided by 2 plus gamma minus 1 m2 square and 1 by 2 power of the entire term. So now we also obtained the value for P2 by P1 as well. Okay, then comes another important parameter, which is actually ratio of densities. So we also know from ideal gas equation P is equal to rho RT. So from here I can say that P2 by P1 will be equal to rho 2 by rho 1 multiplied by T2 by T1. Okay, and simply I will get rho 2 by rho 1 is equal to P2 by P1 times T1 by T2. Okay, so let's now try to find it out. So from here I will get rho 2 by rho 1 is equal to P2 by P1 is M1 by M2 times 2 plus gamma minus 1 M1 square upon 2 plus gamma minus 1 M2 square whole power 1 by 2 multiplied by T1 by T2. So T2 by T1 is this one. So I have to just take the reverse of this. So 2 plus gamma minus 1 into M2 square divided by 2 plus M1 square. Okay. So ultimately what I will get? I will get that rho 2 by rho 1 will be equal to M1 by M2 times, and here it will become 2 plus gamma minus 1 M2 square whole power 1 by 2. So from here I have obtained the ratio of density as well. Okay, so now only one parameter is left which we need to determine, and that particular parameter is nothing but our stagnation pressure, because stagnation temperature is remaining the constant. So we know that stagnation pressure by P is nothing but equal to 1 plus gamma minus 1 by 2 m square and whole power gamma by gamma minus 1. Okay, so now my aim is to calculate P naught 2 by P naught 1. So what I can do, I can do first find out P naught 2 by P2, and then I can find out P naught 1 by P1, and then I can multiply it with P2 by P1. Okay, so let's do this. So if I do so, P naught by P2 will become 2 plus gamma minus 1 into M2 square. Is this point clear? Divided by 2 plus gamma minus 1 into, and this whole power will be gamma by 2 actually cancelling in the numerator and denominator. Okay, and multiplied by P2 by P1. What is P2 by P1? Just now we have calculated. P2 by P1 is M1 by M2 times 2 plus gamma minus 1 M1 square power 1 by 2. Okay, so if you see, if you compare the first term and the second term, okay, so you will be finding in the first term I have M2 in the numerator, here M2 is in the denominator. So basically if I take the reciprocal of this, then this power will become minus 1 by 2. So I can say that the power of this common base can be gamma by gamma minus 1 minus of 1 by 2. Okay, so this will become 2 gamma minus gamma plus 1 divided by 2 times gamma minus 1. Okay, and from here I will get gamma plus 1 by 2 times gamma minus 1. So this is my power. So now from here I can say that P naught 2 by P naught 1 equal to M1 by M2 times 2 plus gamma minus 1 M2 square divided by 2 plus gamma minus 1 M1 square, and whole power is gamma plus 1 by 2 times gamma minus 1. Okay. Is this point clear? So from here we are also able to calculate the value of stagnation pressure. So it means that by utilizing all these parameters, if I know Mach number and friction factor, then I will be able to calculate the downstream Mach number M2, and then once downstream Mach number M2 is known, then all my parameters like ratio of stagnation pressure, ratio of density, ratio of static pressure and static temperature are involving nothing but M1 and M2. Okay, so if these two parameters are known, I can predict all the values. Okay, now we will try to little bit move towards the concept of entropy change during this particular process, because that entropy change will try to give us more physical inferences about the phenomenon which is happening over here. Okay, so let's move towards entropy change, and with that then we will once again come back to these equations to make the physical inferences. So let's consider that I have state 1 at the starting point, and at the exit basically what will be happening, depending upon the length I can get any value. Okay, so say if this much is length, then say if this is my S2, if I increase the length, then I can have some another S2 dash value. Here if I decrease length, then I can have some another S2 double dash value. So what I am doing at the moment, I will start with considering the generic case where I will consider that initial state is designated by 1 and final state I will not give any number, I will simply write the final property value S. Is this point clear? So what I am saying, because depending upon the length I can obtain different exit states. Okay, so what I am doing, if I keep my length as a variable parameter into this formulation, then obviously my entropy will be a variable parameter. So I will not designate it to a particular station, rather I will keep it as a open variable. Is this point clear? Now we know from the first law of thermodynamics that or even I can say that first thermodynamic property relation. So from the first thermodynamic property relation, we know that TdS is equal to du plus PdV. Is this point clear? So this is something which we know from our first thermodynamic property relation. So now this dV can be written as d of 1 by rho, and if you do solve this, it will become minus d rho by rho square. Okay, so it means that my relation will become TdS is equal to du minus P by rho square into d rho. Okay, now I also know that P is equal to rho RT. So P by rho I can write as nothing but RT. Okay, so this I can write as du minus RT into d rho by rho. Okay, now this du also for calorically perfect gas I can write Cv times dt. So let me now divide throughout by T. If I do so, I will get ds will be equal to Cv dt by T minus RT into d rho by rho. Fine. Sorry, T will cancel out because I am dividing throughout by T. Now let me integrate this equation. So I will take starting point as 1, but ending point I am keeping as generic open point. Okay, so integral because R is constant, Cv is also constant for calorically perfect gas. So from here I will get that S minus S1 will be equal to Cv times ln of T by T1 minus R ln of rho by rho 1. Okay, and simply I can say that S minus S1 is equal to Cv times ln of T by T1, and this I can write plus R ln of rho 1 by rho. Okay, So inside actually I have swapped the terms. Now I know that rho 1 into V1 is equal to rho into V. This will be from my continuity equation. So from here I can say that rho 1 by rho I can write as nothing but V by V1. So from here I will get S minus S1 will be equal to CV times T by T1 plus R ln of V by V1. Okay. Now from energy equation I know that Cp times T plus V square by 2 is nothing but equal to Cp times T naught. This point is clear. So interestingly I can write V square as nothing but 2 times of Cp into T naught minus T. Let me substitute this in place of V. So it will be square root of 2 this one. So S minus S1 I can say that Cv times ln, sorry here I have missed one ln. So this should be ln of T by T1 plus R, and here I will get ln of, in place of V I will get say 2 Cp into T naught minus T. Here I will get 2 Cp into T naught minus T1 and whole power 1 by 2. Fine. So this 1 by 2 m to power n, so this I can take outside. So I will get from here that S minus S1 will be equal to Cv times ln of T by T1 plus R and by 2 ln of 2Cp will cancel, T naught minus T divided by T naught minus T1. Fine. Now let me divide this equation throughout by Cv. So if I do so, what I will get, S minus S1 by Cv equal to ln of T by T1 plus in R by Cv. In place of Cv I can write R by gamma minus 1. Okay, because what is Cv? Initially we have derived R by gamma minus 1. So in place of Cv if I write R by gamma minus 1, R will cancel, I will get gamma minus 1 by 2 into ln of T naught minus T divided by T naught minus T1. Okay. So interestingly, from this particular equation we get an idea that if I have friction involved, then what will happen? We know that from the generic equation of entropy, ds is equal to del q by T plus delta S generation. Is this one clear? Now when we are considering the flow with friction, our delta Q is 0 because we are having adiabatic situation. No heat addition, no heat removal. So delta Q will be 0. So it means this ds, whatever entropy change we are calculating for flow with friction, that is equal to delta S generation. And delta S generation is always greater than equal to 0. So it means that ds for the flow with friction has to be greater than equal to 0. So it means that whatever this S minus S1 we are calculating, this always have to be greater than equal to 0. Okay. So this is very clear that whenever a fluid will be flowing inside a pipe with friction, its entropy will always increase. This is one important conclusion which we have made over here. Now we have to see that what is the limiting value up to which its entropy will increase. So if you say that there you are having infinitely long pipe length, then will it go to infinity? So that is something which we have to actually determine over here. Okay, so to determine the limiting value, what we will do, we will try to calculate d of delta s, means d of s minus s1 divided by dt, and we will make it equal to 0. Okay, or in another sense, let me pose it in another way. This is one important equation which relates the temperature and entropy. Okay, this equation, what it is doing, it is relating your temperature and entropy over here. Now if s minus s1 you call nothing but as your delta s, so it is relating your temperature and delta s. Now if you take this particular equation and if you plot it on temperature and delta s axis, okay, you will find this equation will give you curve something like this. Okay, what I have just now said is that this is nothing but an algebraic expression. Okay, what is this? This is just an algebraic expression. So from this algebraic expression, if you know the value of t, corresponding to each t you will get some value of s, or corresponding to one delta s, if you take this as delta x, you can calculate the value of one t. Okay, so if you plot this particular equation on t and delta s diagram, you will get a curve something like this. As this type of flow situation is known as Fanno line flow, this particular curve is also called as Fanno curve. Okay, now, so what I am saying over here, that this curve is nothing but the graphical representation of this particular equation. Is this one clear? And this particular equation will change if I change the value of mass flow rate. So over here, this particular equation is on per unit mass basis. Okay, so if I have to calculate this for given mass of the fluid, so then that will get multiplied with it. Okay, so it means at the moment I can say this is for valid for some particular mass flow rate m1. Okay, now interestingly, one point we are observing, when we have actually plotted this equation on T delta S curve, somewhere over here we are having nothing but the point of maximum entropy. Like I told you that what is the limiting value for maximum entropy. Okay, so say if I start from this point, if in my initial point is this, then along the length of the pipe I will see that along this direction my entropy will increase. If I am at this point, then along this direction my entropy will increase, but ultimately it is reaching to a maximum value, and from there then it is actually saturating, it is not going further ahead. Okay, so we have to now determine that what is this limiting point. So corresponding to this limiting point, if you see over here, we will get nothing but d of ds by dt is nothing but equal to 0. Okay, so this particular slope along this direction has to be 0 at this point, because this is kind of a critical point or inflation point over here. So if I calculate this from this particular equation, then I will get so CV I will just remove, because ultimately, okay, let me take CV also on the right hand side. Okay, so if I take this derivation, then what I will get? I will get CV times 1 by T CV times 1 by T ln of T by T1. What I will get? Ln of T minus ln of T1. So derivative of ln of T will be nothing but 1 by T, and derivative of ln T1 will be 0, because T1 is a fixed parameter. Okay, so this will become 1 by T plus gamma minus 1 by 2 times derivative of ln T naught minus T will become 1 divided by T naught minus T into derivative of T naught minus T, which will give us minus 1, and derivative of T naught minus T1 will be 0. Okay, so it means this whole has to be equal to 0. So CV, if I take other side, that will be 0 only. So from here I will get 1 by T is nothing but equal to gamma minus 1 by 2 times T naught minus T. Up to this point, is it clear? Now from here simply I can say that 2 times of T naught minus T is equal to T times of gamma minus 1. Okay. Now what I will get, let me multiply and divide both sides by, multiply on both sides by Cp. So I will get 2 times of Cp into T naught minus T and Cp times T into gamma minus 1. Okay, so I have multiplied on both sides with T. So this 2 Cp T naught minus T is nothing but V square. And in place of Cp, I can write gamma R by gamma minus 1 into T into gamma minus 1. Gamma minus 1 is cancelling out. It is becoming equal to gamma R T, which is nothing but equal to A square. So from here I am getting Mach number square is equal to 1, or ultimately Mach number is equal to 1. So it means that corresponding to the point of maximum entropy, our Mach number has to be equal to 1. Up to this point, is it clear? So a simple correlation we have got is that first this entropy equation we have plotted on temperature and delta S axis, and then this, when we have plotted on temperature and delta S axis, we have tried to find out that what is the condition corresponding to the maximum enthalpy point. So from this we have come to know that corresponding to the maximum enthalpy point, our Mach number is nothing but equal to 1. Okay, so it means that now as I told you that when we are taking a pipe, okay, so along the length of the pipe entropy will keep on increasing, and it will increase up to a critical limit when its entropy is maximum and corresponding Mach number is equal to 1. Okay, and if you take that your pipe is having length more than that, then something else will happen. Okay, so if say in your pipe at some point of time in the intermediate zone only Mach number is becoming 1, and after that point if you expect that flow should further progress, then something else will happen actually, because entropy has reached corresponding to its maximum limit, and if you go further then entropy cannot decrease. I will discuss this point in more detail. Before that, let me explain you one more point. The another important point is, when I have this temperature and delta S diagram, and this is my curve, one interesting point for the Fanno line flow is that our T naught is equal to constant. Okay, so T naught is always constant. Now if T naught is constant, what will happen? I have two branches of this curve over here. Okay, so if this is my T naught, this is static temperature for a given situation. T naught will include nothing but the static temperature plus kinetic energy, and kinetic energy will be having more magnitude for nothing but the supersonic flow situation. Okay, so from this curve I can simply say that the branch of this curve which is having low static temperature value, that will be nothing but be having more amount of kinetic energy in order to reach the constant stagnation temperature. So I can say this particular branch over here is nothing but corresponding to the supersonic flow situation. Is this point clear what I am saying over here? So T naught is stagnation temperature is constant, and It is nothing but equal to Cp times static temperature plus V square by 2. So out of these two branches, Cp times of T is less for this branch. So it means if it has to reach to the same value of T naught, it should have more amount of kinetic energy. Okay, and this is also in other sense making sense, because supersonic flows are nothing but high speed flows. So these will be having more contribution of the kinetic energy. So more contribution of kinetic energy is required to reach same stagnation temperature for this lower branch of the curve. Okay, so that's why this lower branch is applicable nothing but for the supersonic flow, and this upper branch will be applicable for subsonic situation. Is this point clear? Now, if in both the branches you are starting at this point, say if you start at this point for subsonic situation, you will find that your entropy of the flow will keep on increasing, and this entropy will reach a maximum value when your Mach number is 1. So this is the limiting situation. So in case of a subsonic flow, we can say that the Mach number of the flow basically increases. If you are having subsonic flow involving friction, then Mach number of the flow will be increasing, and ultimately it has to limit to nothing but the sonic condition. It cannot go beyond sonic condition. And if you have a supersonic flow situation, in case of supersonic flow situation, if you start at this point, if you move along the length of the pipe, say if your length is L1, corresponding to that, say you are getting this point. If you further increase length to L2, then you will get this point. And if your length becomes the maximum possible length, then you will get nothing but your Mach number is equal to 1. Fine. So interesting point is that in case of subsonic flow situation, you are starting with Mach number less than 1, and your Mach number at 2 is actually increasing. So as you move along this length, your Mach number is increasing, and what is the limiting value for this? Limiting value for M2 is nothing but 1. It has to saturate at 1. And if you take the supersonic flow situation, then you will be finding M2 will be less than M1. As you move along this line, your Mach number is actually decreasing, and for limiting value, M2 is once again becoming 1. Okay, it is limiting to reaching to a value of 1. Interestingly, you can also see from this curve only, here static temperature is actually decreasing for the case of a subsonic flow. So T2 over here is actually less than T1, and whereas for the case of a supersonic flow, T2 is greater than T1. Okay, we will also find that in case of supersonic flow situation, that P2 will be greater than P1, and rho 2 will also be greater than rho 1. Sorry, I have written something wrong. Here this T2 should be less than T1. For subsonic flow, T2 will be less than T1. Okay, and also P2 will be less than P1, and rho 2 will be less than rho. So that is something which we will get for subsonic flow, and for supersonic flow, T2 will be greater than T1, P2 will be greater than P1, and rho 2 will be greater than rho 1. And in both cases, T01 will be equal to, stagnation temperature has to remain constant. And another interesting fact is that rho 01 will be greater than rho 02 for supersonic case, and for subsonic case also it has, sorry, not rho, P01 has to be greater than equal to greater than P01 for the case of a supersonic flow, and this will be applicable for subsonic flow as well, because for the flow to occur, your upstream stagnation pressure has to be more than the downstream stagnation pressure. So is this point clear? Up to this point, is it clear? So what will happen for subsonic flow situation and what will happen for supersonic flow situation, two different properties. That is something which we have seen over here. But still now, still it is not very much clear to us that how this Mach number is equal to 1 physically depicting, what physically it represents. Okay. So to give the more idea, I will take one more illustration. Before that, one interesting point I would like to highlight over here to you, that if you consider a subsonic flow situation, okay, so what happens in a subsonic flow situation? We know that we will be having formation of a boundary layer inside the pipe. So this boundary layer actually along the length of the pipe will keep on growing, and we will see within the boundary layer our velocities are very small, and in between this our velocity is nothing but equal to high velocity. Okay, so not free stream, because for continuity equation to balance, our area is decreasing, that velocity has to increase. So here we will be having higher velocity. Okay, so ultimately you can see that basically in this particular zone which is at the core, I can consider this boundary layer region almost a stagnant situation where fluid is almost stationary, and in this central region I will be having nothing but the high velocity. So as area along the x direction is actually decreasing, that's why our flow velocity and the Mach number actually will increase. Okay, so for subsonic flow situation. Okay, now I will once again come back to this point actually. M naught equal to 1. So to further explain this, let's consider one interesting point. Let's consider that I have a pipe, and in this pipe I am starting at some Mach number 1, and this L max is my maximum length of the pipe. Okay, L max is my maximum length of the pipe, which is giving me this M2 Mach number as equal to 1. So it means that I have started at some point and then finally I have reached at nothing but the sonic condition. Now what if I do? If I take some additional length in this pipe, this I have taken some additional length. Okay, so this is the L max which is giving us nothing but the sonic condition. Now more than this, what we have done, we have extended one some additional length over here. So it is pretty much clear to us. So say if I have to write down delta S total over here, so total entropy will be nothing but delta S from point number 1 to sonic condition plus delta S for the additional region. Okay, now it is very much clear to us from the previous entropy change equation that maximum entropy we will get nothing but corresponding to the sonic condition. Okay, so here only I will be having the maximum entropy point. So it means that this is my maximum or limiting condition of entropy. Okay, so after this, if I have to follow this curve, okay, so say if I start from this point, so I have reached to maximum condition. Now if I have to follow the same curve, then I have to move along the path of decreasing entropy. Contrary, if I start at this point, then in the L max region I will reach to this point, and if I have to further follow this curve, then I have to actually take this path of decreasing entropy. Okay, is this point clear? So in both the directions what is happening, if I start at this point, then also I am reaching to maximum entropy, and if I have to further move along the curve, then I have to move in the direction of decreasing entropy. Here also if I start at this point, I will go up to maximum entropy, and then if I have to follow the curve in subsonic side, then I have to move along the path of decreasing entropy. Now it means that if I have to follow the same curve after reaching the maximum condition, this delta S additional has to be negative. Then only I can follow that particular curve. Okay. Now, just now also I have shown you that ds is equal to del q by t plus delta S generation. For flow involving friction under adiabatic condition, this is equal to 0. Delta S generation will always be greater than equal to 0. So it means that this negative condition is something which is not possible. Okay. So now it is important to make one clear difference. In case of Rayleigh curve, what we have done? In case of Rayleigh curve, we said that if I start from supersonic point, if I keep on adding the heat, I will reach a point of sonic condition, and from this point if I have to follow the curve, then in place of adding heat, in the remaining portion of the length of the pipe I have to cool. If I start cooling, then I will be actually able to reverse the direction of entropy. Okay, because in that case if I am removing heat out of the fluid, then del q by t term will be negative, which can decrease the entropy value, and I can follow this curve. Okay, whereas in case of friction, direction of friction cannot be reversed. Okay, if you move from left to right or right to left, friction will be the always having nothing but effect of increasing entropy. You cannot expect from friction that it will actually decrease the entropy. So it means that it is interesting to know that on a Rayleigh curve, if I start from supersonic point, by adding heat I can reach to a sonic condition, and then by removing heat I can reach to subsonic condition. Similarly, if I start from subsonic point, I will reach to sonic condition by adding heat, then by cooling I can follow this curve and reach to supersonic situation. But in case of Fanno flow, we will never be able to. If we start at supersonic point, the limiting condition is I will reach to only the sonic condition. I cannot go into the subsonic region. Is this point clear? So now what I said that this was my limiting condition, and if I have taken this additional length, then this additional length, what it will do? It will not give us negative entropy. It will give us some positive contribution of entropy. Okay, so if positive contribution of entropy is coming, so what will happen? Let me now represent it on graph. Now what will happen? This was your point corresponding to say Mach number equal to 1 when you have say mass flow rate of fluid as m1. So what I have said now, that this particular additional portion will give us the more value of entropy. So in this zone we will get more value of entropy. So if more value of entropy is coming, my curve will shift somewhere towards right. Is this point clear? Because entropy value is increasing with this additional length portion. So but once again, this point is remaining at nothing but Mach number equal to 1 only, because highest entropy point from the nature of the equation or nature of the curve, it has to always reach corresponding to Mach number equal to 1. So now you can interestingly see in this particular portion with Lmax length you are able to reach the m1.2 sonic condition. Now when you have taken that new curve, then your length is greater than Lmax, and then you are reaching from m1 condition to 1. Okay, so in this situation what will happen, basically we will experience that inlet condition will get modified. So here you can see this was the initial inlet condition, now this is our inlet condition. Okay, and this will get adjusted to some new mass flow rate. m2 dot. So if this was the mass flow rate, this curve was corresponding to mass flow rate of m1 dot, this will shift to some new mass flow rate of m2 dot, and this m2 dot over here will be less than m1 dot. Is this one clear? So it means that if you keep on moving your Fanno curve towards right, so when your length is increasing, your Fanno curve will keep on shifting towards right, but always it will be having Mach number equal to 1 at the critical condition, but this initial condition will keep on changing. Okay, and as this initial condition is keeping on changing, your mass flow rate also will adjust to some new value, and when your length is increasing, mass flow rate will keep on decreasing. Is this point clear? So this is one important finding, that if we keep on increasing the length, then basically what is happening to my Fanno curve. Okay, up to this point, is it clear? Now we have so ultimately let me give you some physical idea. So in case of basically supersonic flow, what happens? In case of subsonic flow, what happens? When molecules feel that some additional length is coming, okay, so they pass this information to the inlet, and they keep on modifying the inlet condition, they adjust the inlet condition. That is something which happens in case of subsonic flow situation. But if you are having the supersonic flow situation, then what will happen? When molecules will feel that they are getting some additional length, they will try to pass this information towards the upstream direction, okay, but our flow velocity is higher than the speed at which molecules are transferring this information to the leftward direction or upstream direction. So what will happen? These molecules will actually pile or coalesce at some particular location, and there they will form nothing but a shock wave. Okay, so in case of subsonic flow, what happens? In case of subsonic flow, basically the inlet condition get modified, whereas in case of supersonic flow situation, what will be happening? This condition will be adjusted by the presence of a shock wave within the duct. So basically shock wave will modify the property, that will create a discontinuity in the flow situation. Okay, and what will be the location at which shock wave will form, that depends upon the exit pressure of the pipe and how much is the additional length actually that is beyond the Mach number equal to 1. So basically back pressure at the exit of pipe governs nothing but the formation of shock wave. So maybe at this point we will not take up this particular process in more detail, but in the subsequent lectures, when I will be specifically referring to the converging diverging nozzles and quasi one dimensional flow in enclosures, then we will take up this concept in more details. Okay. Okay, so next point, now let me go back to my equation number 1 again. Okay, so from equation number 1, if our L is the length, then we were able to get some Mach number M2. Okay, however, it is very clear to us now that we have some Lmax value here, corresponding to which for a given mass flow rate, my M2 Mach number is nothing but 1. Okay, so let's try to see for Lmax how this equation behaves. Okay, so I will get 4 F bar Lmax by D, that will be equal to minus of gamma plus 1 by 2 gamma, and this will become ln of M2 will become now 1, because we are considering limiting situation. Okay, so 1 by M1. Okay, next
bracket 1 minus 1 by m1 square plus gamma plus 1 by 2 gamma ln 1 plus gamma minus 1 by 2
1 plus gamma minus,
1/2.
so that will become 2 plus gamma minus 1. So ultimately that will become 2 plus gamma minus 1, and ultimately it will become gamma plus 1. So here I am getting gamma plus 1. So this gamma plus 1 is coming after I am substituting m2 equal to 1, and then in the denominator I will get, so this I am taking 2 LCM. So here also let me take 2 LCM. So I will get 2 plus, okay, is this one clear? How this has come? Or anyone is having any doubt? This point is clear? Nothing but I have substituted over here m2 is equal to 1. So this is my important equation. Now from this equation let's try to make the inferences. If I consider the case of m1 equal to 1, what I am getting? One by ln of 1 0, 1 minus 1 0. This will become gamma plus 1 by gamma plus 1, ln of 1 equal to 0. So it means that if my upstream Mach number is equal to 1, corresponding to that I will get, and if I am having the L max, maximum length possible, corresponding to that I will get 4 f bar L max by ds. Okay. Now let's consider the case of a very high Mach number m1 which is approaching to infinity. Very high Mach number. So here what I will do, if I calculate this, you can see from here that gamma plus 1 by 2 gamma is common in both these terms. So I can write this as gamma plus 1 by 2 gamma times ln of, if this is say m, so ln of gamma plus 1 divided by 2 plus gamma minus 1. So we have to do m by n. This is my n. So n is becoming nothing but 1 by m1 square. Okay. And minus of 1 by gamma into 1 minus. So now you substitute m1 to infinity. So if you substitute m1 to infinity, my 4f bar L max by d becomes gamma plus 1 by 2 gamma ln of, here 2 by m1 will become 0. This will become ln of gamma plus 1 by gamma minus 1. Okay. And minus of this 1 by infinity will become 0, minus of 1 by 2. Can you tell me for air at standard condition having gamma equal to 1.4, what is this value? Please calculate and tell me. Please tell me this value, how much it is coming. Point 821. Okay. So I am getting from here this value equal to 0.821. Another important point is that when our Mach number is when our Mach number M1 is very small, say in the range of 0.01 or whatever smaller values, corresponding to that I will be getting 4f bar L max by D as nothing but a very high value. Okay, you can try this. You substitute this value, you will be finding a very high number over here. Okay, so from here we get one interesting curve, 4f bar L max by D versus upstream Mach number M1. Okay, so say this is my Mach number 0, then I will be having value increasing. Say this is Mach number equal to 1, and this is say Mach number as very high as 10. Okay, so what I will be finding here, I will be having very high value of the 4f bar L max by D, and this value will keep on decreasing. It will reach a minima at 1, where it will be 0, and then further it will try to increase, and finally it will saturate to a value of 0.821. Is this one clear? So here you can say that when your upstream Mach number is greater than 1, then this is the situation of a supersonic condition, and this is the case of a. So it means that for supersonic condition, our value of 4f bar L max by D varies from 1 to, sorry, this is 0 to 0.821. So for supersonic flow condition, always your 4f bar L max by D will be from 0 to 0.821. Whereas for subsonic situation, this can go to very high value, and ultimately it will saturate to 0. Is this one clear? So this is a simple physical inference also. If you take a pipe, upstream Mach number is also 1, downstream Mach number is also 1. So in this situation we will not be having any flow over here. So if we are not having the flow, ultimately friction factor will be 0, a static condition. Okay, because ultimately at the length of the pipe, outstream Mach number we are fixing to 1, and if our upstream Mach number is also 1, so it means properties here are same. So that is the case of a no flow situation, and physically I am getting nothing but a mathematically I am getting nothing but a 0 friction factor over here. Okay, so now I will stop at this point. There are some more points left, little bit about the Fanno flow. What we can do basically, the way earlier I have plotted shock wave over the Rayleigh curve. Similarly, I can transform this Fanno curve from temperature delta S axis to basically Mollier diagram, because that is nothing but a scaling factor will only multiply. And then on the same curve, we will try to see the representation of Rayleigh line, Fanno curve, and the normal shock wave. Okay, for the given flow conditions. That we will take up in the next lecture, and then we will start our discussion on oblique shock waves.